Bismillahirrahmanirrahim. Assalamu alaikum and welcome to part 2 of acceptance sampling. This session will deal with actual problems which are an application of the concepts learned in part 1. So if you have understood those concepts, you will find these problems very easy. So here we go. Let's take a typical acceptance sampling problem. An order for supply of 2,000 electrical fans has been placed on a supplier. The agreed sampling plan calls for a random sample of 120 fans with an acceptance level of 3. AQL has been settled at 2% effectives and LTPD 6%. Find alpha risk and beta risk. Let's find out what data we have been given. This is the lot size, 2,000 fans. 120 fans is sample size, small n, and acceptance level of 3 is C is equal to 3. AQL is 2% or 0.02. By the way, AQL and LTPD could be in the form of a percentage. It could be in the form of a decimal fraction. It could be descriptive, like 10 out of 1,000. In that case, you will have to translate this sentence into a figure. 10 out of 1,000 would mean 1 out of 100 or 1% of 0.01. And LTPD is 6%, and we have been asked to find alpha risk and beta risk. Alpha risk meaning what is the risk for the seller that his good lot will be rejected by the buyer, and for the buyer, what is the risk or the probability that he will accept a bad lot from the supplier. Here are a few considerations. One I have just mentioned those were regarding that this consideration was regarding alpha risk. What does that imply? And beta risk. What does that imply? The second consideration is about these figures, AQL 2% and 6%. AQL 2% roughly equates to 2.3 sigma, quality level 2.3 sigma. So if the seller does indeed produce these deliverables or electrical fans at 2% or 2.3 sigma, then there is a good chance that that his consignment of 2,000 electrical fans will clear the validate scope process. On the other hand, the customer, the project manager is willing up to 6% effectives, but anything beyond that are surely heading for rejection. So that is the scenario, and let's now do this question to find how much risk the seller is facing in the form of alpha risk and how much risk the buyer is facing in the form of beta risk. So I'll just take this data to the next page, the same data. The way to do these questions vary from person to person. I'm going to share with you my way of doing it. You may not follow that, but I have found it to be very useful. And my way of doing such problem is to make 5 columns. In the first column, we list the quality level in the deteriorating order, starting from 0% up to 10%. And we don't go beyond 10%. You already know that the OC curve flattens after 10%, it hits 0. In the next column, we convert the percentage into a sample. That means if an X% is present, if X% defects are present in 100, then how many defects in the sample, which in other words is lambda. So what we do is multiply the sample size, which is 120n, with the probability, with the quality level, which is listed here. So we will have different figures over here. Then we'll enter the, then we will refer to the Poisson tables and enter with these figures, lambda figures, to find out acceptance probabilities. For AQL quality level, we'll find out from the acceptance level, acceptance probability, the rejection probability, and convert it into alpha risk. And likewise for LTPD, we'll find out the acceptance probability, but we will not calculate the rejection probability because that is not required. That acceptance probability will straight away go as alpha risk. So here is the quality level in a deteriorating order, starting from 0%, 1%, 2% is AQL, so we write AQL against 2%, going down, blending into now bad quality, coming to 6%, 6% is our LTPD, and going all the way to the extreme edge, 10%. Next, we multiply this quality level or P with the sample size 120, and we get these figures. It is tantamount to going through a table of 12 because this carries 12. So 12 zeros are 12, 0, 12, 1 is 12, 12 2s are 24, 12 3s are 36. But there is always a chance of making an error when it comes to the decimal place. So I suggest to do at least the first calculation using the calculator. Yes, using the calculator, although it is as simple a calculation as multiplying 0.01 with 120, but there is a chance that you will misplace the decimal. So multiply 0.01 or 1% in case it is given in percentage with 120. And once you have found this to be 1.2, then you can run a 12 times table. If this is 1.2, this has to be 2.4, 3.6 to expedite the matters. Okay, the next step is to enter the Poisson tables with these values of lambda and look for the column header C is equal to 3 and find the probabilities and list those probabilities over here. So let's now go to the Poisson tables. Remember, we have to enter the Poisson table with 1.2, 2.4, 3.6. So you might like to write these figures on a piece of paper before going to the Poisson tables. Otherwise, you'll have to come back to this particular frame of the video. And over here, what I will do is shift the screen to Poisson tables. Here we are. So we have to start with 0. For 0, the probability is always 100%. We established this when we were doing the example on tennis balls. We found that when the number of red balls in the lot was 0, then the probability of finding 2 or less balls was 100. And that is universal, that applies to all cases. So for 0, it is always 1. The first Poisson probability was 1.2. And sorry, what I forgot to mention, the acceptance level here is 3. So we will look into this column, and please remember 3 is in column number 4. 1, 2, 3, 4. So column number 4 is for acceptance level 3. So let's go down to 1.2. 1.2 under 4 is 0.966. Please note it on a piece of paper. Then go down to 2.4. Under 3, it is 0.779. Note it down. And continue going for 3.6. 3.6 under 3 is 0.515. Note it down. And so on and so forth. So with that, I think we can revert to our previous screen. So these are the figures which we have found out. These are the acceptance probabilities from the Poisson tables. Now, we have been asked to find alpha risk. Alpha risk is associated with which quality level? AQL. Here is AQL. And what acceptance probability we have found for AQL? 0.779 or 77.9%. This is acceptance probability. What is alpha risk? Rejection, rejecting something good. So we have to take the complementary of this figure. So if this is acceptance, the rejection will be 1 minus this, which is 0.221. So your alpha risk is 0.221. We always express risks in the form of a percentage. So we say alpha risk is 22.1%. Coming to beta risk, we know that beta risk is associated with the quality level called LTPD or RQL, which is here. What is acceptance probability of that at that quality level? 0.072. You are accepting what? Accepting bad quality, accepting bad quality. This is accepting bad quality. So you don't need to find out anything complementary. This straight away translates to beta risk of 7.2%, and this is as easy as that. So alpha risk, if acceptance sampling takes place according to this plan, the seller would be facing a risk of 22.1%. What risk? That his good lot, this is good lot, will be rejected by the project manager or by the buyer. And the buyer or the project manager will be facing this risk, which is 7.2%. What risk? That he will accept a bad lot. Are these two acceptable? Well, both the buyer and the seller have to refer now to their OPAs to find out what do their company policies say about the risk thresholds. If they are within those thresholds, they'll accept this plan. If not, they will not. So now we will convert this into the OC curve. And for the OC curve, we will plot, if you recall, the quality is plotted along the x-axis and the probability along the vertical axis. And let's do that. This is the same quality, good lot on the left, bad on the right. This is the quality level going from 0% to 10%. And this is the probability from bottom up. And if you recall, for the first one, it was 96.6%. So for the first one, it is 96.6%, and then the rest of the graph. If you recall, the AQL in this case was 2%. So here is AQL 2% hitting the curve going left, which gave you 78% probability of acceptance or 22% probability of rejection, or this is your alpha risk, which is 22%, complementary of 78%, 22%, 78%. You would recall that LTPD or RQL was 6%, which is here. So hit the graph with 6%, and you get a probability indicated over here of 7.2%. So if I can just draw it here, this is your beta risk. And this is your alpha risk. By your, I mean, in this case, your means seller, and in this case, your means the buyer. So that's all about it, really, when it comes to the problems on acceptance fund. I will now go over the effect of changing the values of N and C on the acceptance plan. What happens if you tamper with N and C, or when you change these figures. Change these figures, by the way, you can only change these figures if you have already agreed to an acceptance plan, and then you change NSC, N and C, you have to go to the change control board. So let's now do an example on the effect of changing N and C. Here is an example. A project manager has received a shipment of 1,000 items for the project. The sampling plan for the inspecting these items calls for a sampling size of 60. So sample size N is equal to 60 here, and an acceptance number of 1. That is C is equal to 1, which means you will only accept the lot if in the sample you either have no defectives or just one defective. If there are 2 defectives, the sample is rejected, the lot is rejected. The contract with the supplier calls for an AQL of 1 defective per 100. Now here AQL is given in a descriptive form, 1 defective per 100. You have to translate it into numerical value, so it is 1% or 0.01. And LTPD of 6 defective items per 100, that means LTPD of 6% or 0.06. Construct the OC curve for this plan and determine the suppliers and consumers' risk for the plan. So here is the given data. And now he is asking you, how would the risks, how would the alpha risk and beta risk change if the sample size increased from 60, the sample size is increased to 80, 100, and 120. The acceptance level remains 1. And how will these risks change, alpha risk and beta risk change, if the acceptance level is increased from 1 to 2 to 3 to 4, but keeping the sample size constant at 60. So that is the problem, and we are going to now deal with this. Here is the data. What we are given is big N 1,000, small n 60, small c 1, AQL 1%, LTPD 6%. Let's go to the next slide. This is the data, and this is what we have constructed for N is equal to 60. What we did here, we listed the quality levels from 0 to 10% in deteriorating order. AQL was 1%, asterisk means AQL, this crosshead means LTPD. So 6% LTPD, 1%. And then we multiply this with sample size, which is 60, because in the first case, we are keeping the sample size fixed at 60. Sorry, we are keeping C is equal to 1 fixed and changing the sample size. So you multiply using the calculator. I'll strongly recommend again and again, use the calculator for the first calculation. Don't do it manually. So 60 multiplied by 0.01 gives you 0.06. And once you have found the first one, you can now run your 6 times table. 6 ones are 6, 6 twos are 12, 6 threes are 18, because now you know where to put the decimal point. Next step, we go to the Poisson tables and enter these values of lambda to find the probabilities of acceptance. So let's do that. Change the screen. Go to the Poisson tables. Remember, our first lambda value was 0.06, and the acceptance level was 1, and 1 is in the second column. 1 is in the second column. 0.06, we get a figure of 0.878. The next was, so you can write this down on a piece of paper. For 6, we get 0.6 we get 878, for 1.2 we get 0.663, and so on and so forth. And let's go back to our slide. And here we are, 0.878 and 0.663, and you can find the values for the rest. Okay, this is acceptance probability. What is rejection probability? 1 minus this, which will come to 0.122, and rejecting something good at AQL is alpha risk. So 1 minus 878 is 0.122 is equal to 12.2%, which is alpha risk. Coming to beta risk, that is accepting something bad at LTPD, which was 6%. We get a probability of accepting a bad lot of 12.6%. So that is our beta risk. Now, in the next columns, what we are going to do is change the value of n from 60 to 80 to 100 to 120 and see what happens to these risks. And these are the figures. And just to reassure you, let's go to Poisson tables again, and this time read for lambda value n, for lambda value 0.8, because 80 minus 1 is now, 80 multiplied by 0.01 is now 0.8. Again, done by calculator, and then you run a times table, 8 times tables this time, because it is 80, 8 times table, 8 ones are 8, 8 twos are 16, 8 threes are 24. And just to reassure you, let's check whether this value is correct. So enter your Poisson table at 0.8 and look under 1, shift screens. .8, 0.809. So that indeed is the case. And I think we can trust the rest, the other figures also. So back to the previous screen, 0.809, remember that is the figure, and you find 0.809 here, which gives us alpha risk of 19.1%, 7.736%, alpha 26.4%, alpha 33.4%. So what conclusion we draw? If we keep the acceptance level the same and increase the sample size, the alpha risk increases. That means increasing the sample size is to the disadvantage of the seller, to the disadvantage of the contractor. Let's look at the beta risk. At 6%, it was 12.6%. For 60, for 80, it reduced to 4.8. For 800, it reduced to 1.7. And at 120, it reduced to 0.6%. Conclusion, increasing the sample size while keeping the acceptance level constant is to the advantage of the buyer, because it reduces the buyer's risk, as you can see from these figures. Let us see how does the situation look like on the OC curve. This is the original curve at n is equal to 60, c is equal to 1, which was the baseline. We have now increased the value of n from 60 to 80 to 120 and 1, and you will see this graph shifting to this side. And thus, just watch the risk. This is the buyer risk. See what happens to this risk as the graph moves to the left, and what happens to this risk. Remember, this is alpha risk. And see what happens to this risk as the graph moves towards higher values of n. And here we go. This is for 80, 100, and 120. Let's look at beta risk. It was initially this, and with increase in sample size, it reduced to this, then this, and with purple, it almost became 0. Look at alpha risk. It was initially this risk. With black, it increased to this much. With green, which is n is equal to 100, it increased to this much. And with purple, which is for n is equal to 120, it has increased to this much. So here again, it demonstrates that as the sample size increases, it is to the gross disadvantage of the seller and to the advantage of the buyer. Let us now keep the sample size fixed and change, or rather increase, the acceptance level. So the same problem, but in this case, we are keeping n 60 constant and changing this. So the next table would be for c is equal to 2, 3, and 4. So before I present that, let me go back to the Poisson tables because this will be easy to consult. We will enter the Poisson tables at 0.6 and C under C is equal to 1. What is the value? Under 2, 3, and 4. So let's change the screens, or rather, let me show you this, all the data first, and you will very clearly see this pattern now. So let's now change the screens. Poisson tables. Okay, 0.6. Here is 0.6. And what is the value under 1? 878. Value under 2? 0.977. Value under 3? 0.997. So do you see the values increasing? If these values are increasing, these are the acceptance probabilities. By the law of complementary values, the complementary values now reducing. This would be 12%, 2%, 0%, 0% here. So you see the alpha risk reducing. Let's go down and find out for beta. Remember, it was 6%, so 6 are 86. And see what is happening to the beta risk. 12.6%, 30.3% for 2, 51.5% for 3, and look, a whopper 71% under 4. So now let's go back and to see those values again. See, 12.2%, 2.3%, remember 0.997 and Z. So alpha risk is reducing at a very gentle pace from 12% to 2, then 0. But look at beta risk, 12%, 30%, 51%, 71%. And now let's look at our OC curves. This is the original curve, and watch what happens to these risks. Let me draw these risks in a different color. What will be a good color? Okay, let me take green. I hope it is visible. Okay, so I'll draw these. This is your beta risk, and this is your alpha risk. And see what happens to these risks as the graph shifts, OC curve shifts for different value of C. And just watch. C is equal to 2. 3, 4. Let's take alpha risk. This risk was this much. With black, it has reduced to this much. With green, almost zero, and purple is absolutely zero. Take beta risk. With B, it has increased to, with black, it has increased to this much. With green, which represents C is equal to 3, the risk is this much. And purple, which represents C is equal to 4, look how much the risk is. So what do we conclude? That if we keep the acceptance level, it is to the advantage of the seller and it is to the disadvantage of the buyer, rather gross disadvantage to the buyer. The final topic which we are going to discuss in this is how to do the reverse. To find out the values of N and C for given values of alpha and beta risk, or for given thresholds of alpha and beta risk. This process has to be by hit and try. It is very similar to finding internal rate of return. If you recall your first semester course on cost management, you worked out a KPI called internal rate of return. How did you find that out? There are no formulas for that. You did it by hit and try. You started with an arbitrary figure of 15%. And then you tweaked this figure up and down to find out a value of internal rate of return, which yield a net present value of 0. We'll employ the same hit and trial method over here to find the value of N and C. By the way, in Excel sheet, now they have come up with a formula for internal rate of return. Otherwise, in Excel sheet 2, one would do trial and error, or at the most use scenarios to be able to find internal rate of return. So let's now let's now find the acceptance sampling plan using hit and trial method. Here is an example. A project manager is negotiating a sampling plan for procurement of 1,000 items for the project, an AQL of 30 defectives in the entire lot. So here again, AQL is being given in a descriptive form, has been settled, and project managers LTPD 80 or more defectives in the lot. So AQL is 30 out of 1,000, which is 3%, and LTPD is 80 out of 1,000, which is 8%. The seller's OPA says that do not accept a risk of more than 5% that your good lot will be rejected by the buyer. Or in other words, alpha risk is 5%. And the buyer's OPA says do not accept more than 10% risk that you will accept a bad lot from the seller. So beta risk is 10%. We have been asked to find out at least 2 combination figures for sample size and sample acceptance level. Please remember, every contract is a win-win situation. You cannot have one-sided contract. You cannot push the other party against the wall. If this is the declared OPA of the seller and this is the declared OPA of the buyer, these have to be respected. The acceptance plan should yield an alpha risk of no more than 5% and a beta risk of no more than 10%. How do we do it? Well, do we do it by trial and error? Here's the data. But how do we do it? Well, again, there are many methods, and this is the way I do it, and this method has not failed me so far. You can devise any other method, but I'm going to share the way I do it for me. What I do is take a piece of paper and draw two rough lines. Well, here these are shown very nicely drawn, but you don't have to be very artistic about it. You don't have to be accurate about it. You just draw two lines, one line representing the beta risk at the bottom and one line representing alpha risk at the top. In this case, beta risk, buyer's risk is 10%, and beta risk is from the floor, from the bottom upward. So from bottom upward, at this 10%, you don't even need to draw the scale. Just write 10% over here. So 0%, 10%. And over here, somewhere over here, indicate 1 or 100%, and then draw a line 5% below that. So this line represents 95%. So against this, write 95%, and against this, write 10%, as I have done here, 10% and 95%. Okay, for trial and error, which I call tukebazi, it is always useful to make a little table, the trial and error table. What we are going to do in this is make the calculations. In the bottom row, we will use our trial and error sample sizes, and we always start with 100. Just as in the case of internal rate of return, you started with 15%. Here we will start with 100 and then tweak it up and down, remembering the concept that if the sample size is increased, it is to the advantage of the buyer and to the disadvantage of the seller. And if the acceptance level is changed, it is to the advantage of the seller and to the disadvantage of the buyer. So those should be at the back of your mind. In these two rows, we list the AQL and LTPD respectively. Remember, we have been told on the last page that AQL is 30 out of 1,000, which translates to 3% or 0.03, and 80 out of 1,000, which translates to 8 out of 100 or 0.08. In these boxes, we will write lambdas at these values of sample size. So let's start with 100. When we start with 100, the lambda at AQL multiplying 0.03 with 100, we get 3. And the lambda or the Poisson mean at LTPD multiply 0.8 with 100 and we get 8. So we have now got two figures with which to enter our Poisson tables. So let's enter them. Remember, we have to enter at 3 and 8. So we will enter 3, and then what are we looking for? Let me go there and tell you what we are looking for. Remember, alpha risk is 5%. So complementary of 5% is 95%. That means we will look for a value, a probability value, which should be at least 90, that is 95. It should be 95 or more, because we have to plot alpha risk above this line, and by the same logic, beta risk below the red line. Again, because alpha risk is 5%, or the OPA or the buyer's threshold is 5%, complementary of 5% is 95%, 95% probability of acceptance. Because when we say 5% alpha risk, this is the 5% probability of rejection. So if 5% is the probability of rejection, what will be the probability of acceptance? 90%, 95%. And that Poisson tables tabulates probabilities of acceptance, not rejection. So alpha risk of 5% translated into probability of acceptance of 95%. And that is what we are going to look for. So let's now shift our screens back to Poisson tables. Remember, we have to enter at 3 and 8. So let's enter at 3. And now we go across this line. And where do we find probability of acceptance of either 95%, or if that is not available, then next higher? Obviously, there is no 95% here. So the next higher is this, 0.961. Okay, if this is what is the next higher, let's see what is this value of C. And we get a value of C to be 6 over here. So 966 translates into 6. Sorry, it's not going vertically. So it is 6. Now we have to stay in the same column for finding the other probability. We cannot shift columns. We can't have different values of C for alpha risk and beta risk. It has to be the same. So what we have established is C is equal to 6. Now we will go down in the same column, 6, and enter Poisson tables for LTPD, which was lambda for LTPD, which was 8. So let's go down to 8. This is 8. And we get a figure of 0.313. So 0.313 and what was it, 966? 0.38 and 0.966. So go back to the screen. We get 0.966. So we plot 0.96. We are at n is equal to 100, 0.966. So this is above this. So we plot it here. So we have satisfied alpha risk. Have we satisfied beta risk also? No. Why? Because this is where the beta risk is. So this acceptance plan, n is equal to 100, C is equal to 6, is not acceptable. Well, it is acceptable to the seller, but not acceptable to the buyer. We have to bring beta risk out of this area, what I may call ilaqai ghair. We have to pluck him out of ilaqai ghair and bring him to the settled area over here. We know that if we have to reduce the buyer's risk, we must increase the sample size. So how much we need to increase? Well, we find that it is almost 25% into this area, no-go area. So how much we should increase? Well, here that's where your experience, your reflex action, your intuition would come in. You can use any value. You can use, if it is, you can argue that, look, it is about 125%. So let me increase it to 125 by 25% to 125% or 130. But I'm afraid it's not linear. You saw it, the curve is not line, it is a curve. You have to be a little innovative, little bold in your choices. I have the benefit of the hindsight, but I'm sure when you do this exercise, you will think likewise. In this particular case, you have to make a bold increase in the sample size, maybe go all the way to 200, maybe 180, maybe 160, try 140. but anything less than that would be meaningless. So let's see what I have done. I've selected 200. So my next tukka is 200. So lambda at 200, 200 multiplied by 0.03 is 6. And lambda at LTPD becomes 16. Sample size has doubled, so has the lambda. Okay. Let's now revert to the Poisson tables again. And we will now enter the Poisson tables initially at 6 and then initially at 6, find the column, find the value of C, and then come down and enter the table at 16. So 6 and 16, remember that. Let's go. Change the screen. So 6 and 16. 6 and 16. Here is 6. Here is 6. What are we looking for? A probability of 95%. And if that is not available, the next higher. So let's look at this line and we get a probability of, well, this is lower, this is higher, so we select this, 95.7. What column is this? 1, this is for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or let's go up and find out if this indeed is 10, or go down for that matter. 957, 957, yes, it is 10. So C is equal to 10. So we'll maintain this column, go down and see what is in column C, in column 10 for lambda is equal to 16. So lambda is equal to 16 is here. Lambda is equal to 16 and under 10 we have 0.77. So 0.77, the top probability was 0.957 and this bottom probability is 0.077. Okay. Let's go back and plot these two probabilities. I hope you have noted them down on a piece of paper. So n is equal to 200. We got a value of C is equal to 10. Let's plot. We get 0.957, which is higher, so alpha risk is satisfied. And lo and behold, we find this to be below red line, because this is 0.010%, this is 7.7%. Bingo, we have got our acceptance plan. That means this is a plan, n is equal to 100, C is equal to 10, which satisfies both the buyer and the seller. Now, having found the datum or something to work upon, we cannot tweak this figure of 200 less and more. So we'll go down to 120. And if 120 is also satisfied, we'll go down to 160. If that is also satisfied, we'll go to 140. We'll continue going down till such time we find that it is no more satisfactory. And then we'll come back to 200 and start increasing to, let's say, 210 or 220, 240, 260, etc. So our next tukka will be 180. Let's tweak it down first. When we tweak it down, we find that lambda at LAQL becomes 5.4, 0.03 multiplied by 180 is 5.4. Again, I stress, use your calculators. And 0.08 multiplied by 180 is 14.4. So let me take note of this. We will have to enter at 5.4 and 14.4. Okay, time for Poisson tables again. So we enter at 5.4 and we have to find a probability of more equal to or more than 95.1, and here we find 0.951. This is less, so this is the one, 0.951. So 0.951, and this is for C is equal to 9. Now we have to remain in this C is equal to 9 and enter the Poisson tables at 14.4. Where was column 9? Column 9 was 1, 2, 3, 4, 5. Fifth column from the right. So let's go up. Fifth column from the right, 1, 2, 3, 4, 5. So our probability here is 0.092. Okay, back to our problem. N is equal to 80. We found C is equal to 9. It was 0.951, so it is above the line. This one was 0.92, so it is still below 10%. Again, this sampling plan is acceptable to both parties. Let's tweak down more. Let's take 160. N is equal to 160. So if N is equal to 160, AQL, it will become 4.8. And lambda at LTPD would be 12.8. 16 8s are 128 and 16 3s are 48. Yes. So let's now enter the Poisson tables at 4.8. Let me note it down. 4.8 and 12.8. So Poisson tables. Okay. First one was 4.8. Okay, 4.8. Okay, it is this value here, 0.975. 0.975, because one to the left of it is slightly less, so we will take this. Next we come to that this is C is equal to 9. So we'll stay in this column and enter the Poisson tables at 12.8 now. $12.8. And in column 9, what do we find? 17.9 or 0.179. So let's now plot this. So back to the problem. Let me put N is equal to 160. C is equal to 9. So our first probability was 0.957. So this is the same as this one here. So we find ourselves here. And the lower probability is 17.9. 17.9 is about here. So we have gone into the no-go area. So we find that this acceptance plan is not acceptable because it does not satisfy the buyer. That means 180 is about the limit. Perhaps there could be 170. I don't know. You have to work it out. But nothing below 160. That means now go on the other side. Go to 220. 220 at 3 would be 6.6 and at 8 would be 17.6. 3 multiplied by 220, 6.6. 8 multiplied by 220, 17.6. So let me take a note of this. 17.6 and 6.6. So back to the Poisson tables. So we have to enter at 6.6. Here is 6.6. Find something bigger than 9.5. This is here. This is column number 11. So 0.963. C is equal to 11. And now we keep this column and go to the bottom with 17.6, enter 17.6. This is 17.6. And under 11, we find 0.065. So now we plot these, go back to the problem. And first one was 963, so it is here, acceptable. This is 0.065, it is here, acceptable. So n is equal to 20, c is equal to 11 is acceptable. And then you do it for 240. Sorry, here we have one, he has done it for here, 160. So that is not acceptable. Next is 240. And again, I don't propose doing it. So this is also acceptable. So this is how we work out a suitable acceptance sampling plan which will satisfy both the buyer and the seller. With that, we come to the end of this subject of acceptance sampling. On that note, Allah Hafiz, thank you very much for joining.